Hey guys, welcome back to another Leetcode video. Today we're going to be looking at Leetcode 560, subarray sum equals k. This is a medium difficulty Leetcode problem, and the problem description tells us that given an array of integers nums and an integer k, we want to return the total number of subarrays whose sum equals to k. And we're given the definition of what a subarray is, which is just a contiguous, non-empty sequence of elements within an array. So basically, the examples tell us everything we need to know, but also the problem description itself is quite simple. And basically in this example, we have the output 2, and that's because we can create, there's two subarrays which sum up to 2, 1 and 1, and 1 and 1, and these both equal to k, which is 2, and so we return the output of 2. So at a glance, this looks like quite a simple problem. So, how could we solve this problem? Well, you might think at first, let's use a hash map. So let's say we have 1, 2, and 3 as an example. Just copying from this example over here. Well, let's use a hash map. So, why not? Let's just use a hash map. So we can say, we have a sliding window. First is equal to 1, then the sum is equal to 3, and k is equal to 3 over here. So perfect, we've found a result. Our result so far is equal to 1, and then we can find another subarray, and now it's equal to 6. So what do? We shrink our sliding window, as you do with a sliding window technique. And now we have a subarray which is equal to 5. So we need to shrink again. We shrink again. And now that we find that we have a subarray which is equal to 3. So we can increment our result by 1, and we get an output of 2. So it works perfectly fine. So why don't we just use a sliding window technique to solve this problem? Well, we're given some constraints, and the constraints tell us that each element in our nums list could be either positive or negative integer between negative 1000 and positive 1000. So a sliding window technique would not actually work. Sliding window technique in this case would only work if we knew that every time we were to subtract or we would shrink our window, we would decrement the sum, and every time we would increase the window, we would increase the sum. But that's not the case with negative numbers because it throws a spanner into the work, so to speak. So to solve this problem, we can't use a sliding window technique. What about brute forcing it? Well, we could brute force it. So let's say we have 1, 2, and 3. How would we brute force this? Well, we could say, start off at 1 and then start off at 1, 2. Okay, we found ourselves a subarray whose sum equals to 3, and then we can look again, and now we found a subarray which equals to 6, but that's not equal to the 3 that we wanted. So we'll move on to the next element. We'll say 2 and 3. So we'll say, 2, no, 3, no. Let's move on to the next element. Oh yeah, we found 3. So now we've found, through a brute force big O of n squared technique solution, we've solved this problem. But it isn't optimal. And why isn't it optimal? Well, let's just have a look at it. All these lines are paths that we've taken, iterations that we've done, and we've reused so much logic. We've done so much computation beforehand. So for example, solving just this iteration for the last iteration that we did, which subsequently gives us 3. Well, imagine we already had this pre-computed and stored somewhere. So then we could just say 6, which is equal to the sum of the whole subarray minus what we've already pre-computed, which is equal to 3 as well, gives us 3, and therefore we can return 3. So what if we were to pre-compute these values over here? Then we would only need to compute the values that we haven't yet computed in previous iterations. This would still be a brute force solution, but it would be slightly more optimal. And so this is the kind of intuition we're going to use to solve this technique. And to solve this technique, we're going to be using a hash map actually. And we're going to be using a technique called a prefix hash map technique. So a prefix hash map technique basically, or prefix sum hash map technique, is when we pre-compute the sum. So let's say we have 1, 2, and 3 again, and we have, pre-computing the sum would give us 1, 3, and 6. This is pre-computing. So each of these is a prefix sum. So let me actually walk through a problem. So let's say we have 1, 2, and 3 again. I am in love with these sequence of numbers clearly. So we want to have our hash map, which is going to be the prefix sum and the count. And we basically want to say, in this example, we have the sum is equal to 6. 6 minus k, so 6 minus k, where k is 3, will give us 3. So if only there was a subarray whose sum equal to k, if only there was a prefix sum equal to 3, well, there is 1 and 2. So we can say 6 minus 3 is equal to 3, and that is, we can now increment our result counter and our result total of how many subarrays sums equal to k. So that's the intuition behind solving this problem. So let's actually walk through the full example. So we want to first initialize our hash map with a prefix 0 with a count 1. And the reason we're going to do this, the reason we have this prefix here will make sense in a bit. But let's say we start off with 1, 2, and 3. So we start off with 1. We say, what's 1 minus 3? It's equal to minus 2. Is minus 2 in our hash map? No, it's not. But we can increment 1 with a count of 1. We could look at 1 and 2 next. 3. Well, 3 minus 3 is equal to 0. Well, there is no subarray sum that equals 0, but we have already initialized 0 to be 1 in our hash map, which is why we did that in the first place. So we kind of best this edge case. So now we can say result plus equals 1. So we can increment our result by 1. Actually, let me just write this in another color. So result equals 1, and we can set in our hash map 3, the prefix sum 3 comes once in so far in our subarray. And then we can move on to the next subarray, which is going to be equal to 1, 2, and 3. Well, that's going to be equal to 6. Well, 6 minus k is equal to 3. Does 3 exist in our subarray? Well, yes, it does. We just computed that. So, and that count is 1. So we can increment our result by 1, and subsequently we get to the end of our list as well. So our result total is equal to 2. So we basically solve this entire problem with a single pass as opposed to using a brute force technique, just by pre-computing the prefix sums as well as their counts. So I hope that description and drawing actually made sense. It can take a while to wrap your head around it, but let's actually get to coding this up, and it'll definitely make more sense as we start coding. So let's set a result equal to 0. This is going to be our result counter. Our current sum, which is going to be equal to 0. This is going to be the current sum of our subarray, of all the elements that we've computed so far. And our hash map. So our hash map is going to be equal to, again, we're going to initialize u as 1. We're going to initialize 0 as 1 for this hash map. So that would best the edge case that we mentioned earlier. And then we can say for each number in nums, current sum plus equals n. And we want to find our difference. Well, that's going to be equal to the current sum minus k. So the current sum minus minus k. So that's our difference. So that we know is our difference that we need to find in our hash map if that difference already exists. So if you've solved Leetcode TSUM, you might say that there are similarities with this with TSUM, strangely enough. So we can say result plus equals, and it's going to be equal to hash map dot get difference if the difference exists. Otherwise, it's just going to be equal to 0. And then we can again set hash map current sum equal to, we can increment the current prefix sum in our hash map so that on the next iteration we can use that if need be. And then we can simply return our result. Let's submit our code. And we can see that we pass all 93 test cases for this problem. So in terms of time complexity, guys, like we mentioned, it's going to be big O of n time complexity, as well as the space complexity also being big O of n, because we could have all the elements in our hash map worst case scenario. So with that being said, I hope you guys enjoyed this video, and I'll catch you in the next one.